In this video, you're going to learn about how resources are allocated inside Kubernetes. Kubernetes has its own abstraction for things like CPU and memory, and we'll see how these map down to the underlying things we've learned about control groups. Before we talk about CPU and memory inside Kubernetes, let's quickly introduce namespaces. Up until now, every cat command that we've done against our Kubernetes cluster has been in the default namespace. Namespaces provide a way to segregate the cluster. Each namespace can have its own access rights, so you might only be able to access certain namespaces within a cluster. Resources can also be restricted per namespace. So we can say your namespace for one particular service is only allowed to use 6 cores and 32 gigabytes of RAM. Certain companies might have a policy of giving a namespace to a team, and then it's up to the team to decide which services to deploy there and how to break up their services. Whereas other organizations will say that a namespace belongs to a logical service. So it might be your user service or your payment service gets its own namespace. We won't use namespaces in the rest of the course. We'll continue to operate in the default namespace. But it's good to know they exist, and all of the resources that you're about to learn about can be limited per namespace. We're going to learn about Kubernetes requests and Kubernetes limits. For every type of resource, memory, disk block I/O, CPU, a pod or a container can request an amount of a resource, for example, 4 CPUs, and a limit. So what's the difference? Request's primary use case is for scheduling. If a pod requests a certain amount of a resource, say 256 megabytes of RAM or 2 cores, it can only be placed on a node that can satisfy that request. However, it's only a request, it's not a limit, which means that if there are more resources available on the host, be them CPU or memory, then that container is free to use those resources. Requests can never result in a container being killed or throttled. Let's see how requests influence scheduling. Imagine we have a Kubernetes cluster with 2 nodes. We've got 6 CPUs on one of the nodes and 4 CPUs on the other. If a pod gets deployed and it has a request of 3 CPUs, it can be placed on either node because both of them have enough. Node 1 has 6 free CPUs and node 2 has 4 free CPUs. Let's say it's deployed on node 1 and then another request comes in. So we've got another pod, a new deployment, and this one has asked for 4 CPUs. Now, because node 1 only has 3 CPUs left, then it can only be placed on node 2. If a third request comes in and it's for more than the available resources in the cluster, then it can't be deployed. With 4 CPUs as a request, it can't be put on node 2 and it can't be put on node 1. This pod would remain pending. So if your pods or your deployments aren't being started and they're in the pending state, it's because of this scheduling. Pods without any requests, so all of the ones that we've seen up to this point, can be placed on any node, and then they'll have the lowest priority for any resources. So for instance, if a pod was to come in with no requests, it could be put on node 2. But then if pod 2, which has made a request, decides it needs to utilize all of those 4 CPUs, then this pod without requests wouldn't get any CPU. You can see the current state of the nodes in your cluster and their capacity by using kubectl describe. Here I've described one of the nodes in my cluster and it has 6 CPUs, it has some ephemeral storage and some memory. Another part of the output of kubectl describe says how much of those requests have been utilized. So in this example, we've used 12% of the CPU, 750 M. M stands for millicore. We'll discuss that in detail in the next video. Think of that as 0.75 of a core have been requested. Limits, on the other hand, are a hard limit of an amount of a resource can be used. For certain resources, such as a CPU, the pod will be throttled. It will be stopped from ever going above its limit. However, for certain other resources, that can't be the case. There's no way that the container runtime can prevent your code running in your container from requesting more memory, from trying to allocate more memory. So in those cases, for resources that can't be throttled and limited, then the pod will be killed. A big difference from requests is that limits are always enforced, even if the box is underutilized. If you say, I want my container to be limited to a certain amount of memory, it won't be allowed to use more. Whereas if you do a request for a resource, if there are free resources on that box, it's able to use as much as it can. Have a think about this. With your knowledge of CPU control groups, how do you think requests and limited are implemented? We'll find out in the next video.